Good afternoon and welcome to the latest installment of Bitgardener's Office Hours. The format of this presentation, if you're a first-time joiner here, we'll do a short presentation, usually 20-ish minutes, and then we will open it up for discussion. Any questions you may have, any challenges you're experiencing in your own facilities, please log them in the Q&A box located in the bottom right-hand corner of your screen. We'll get to them right after the presentation. We are also recording this webinar, and we'll send out the link as well as the PowerPoint to you during our follow-ups. So with that, I'd like to introduce Corey Cohen, our Senior Application Specialist. He'll be walking us through. We also have several members of our regional sales team as well as our business line managers on the line. So you have lots of experts here to help alleviate any problems or issues you're having. So with that, Corey, let me turn it over to you.
Thank you, John, and good afternoon, everyone. So today's office hours, as John mentioned, will be focused on elliptical tolerancing and the evolution of color difference equations. So hopefully everyone in attendance has some kind of background in color, has some knowledge of measuring color and LAD space and things like that. But once you get past the basics of color measurement, one of the major difficulties that can come up is, what do you do with your color numbers? How do you tolerance? How do you set for, how do you decide what to pass and what to fail? And so there have been different ways of tolerancing, and there are different ways of calculating color differences that can be more beneficial for different applications or different materials and things like that. So today we're going to go a bit over elliptical tolerancing, LCH tolerancing, and just sort of how those different color difference equations came about and why and how they can be useful to you. So we'll start with the CLAB system, the LAD coordinate system, and this is how, of course, we describe colors in this three-dimensional space using these three values, or these three axes or three coordinates, which are L, A, and B. So L is lightness, so the higher the L number, the lighter your color. A is for red and green. So if your color has a positive A value, your color has red in it. If it has a negative A value, it has green in it. Similarly with blue, if your color has a positive B value, that indicates it has yellow in it. And if it has a negative B value, it indicates it has blue in it. So we can use these three numbers to describe any color in this color space. And when you take a measurement with your spectrophotometer, this is typically, most often, this is the coordinate system. These are the numbers that you get. You get LAD numbers for your color. So as an example here, we have this orange color, and it has an L value of 58. It has an A value of positive 30. So since the A value is positive, we know it has red in it. And 30 is a pretty high A value, so we know it has a lot of red in it. And the B value is also positive 36, so there's also a lot of yellow in it. So that matches up with what we're seeing. We're seeing a color of a kind of a medium lightness with a high amount of red and a high amount of yellow. And of course, if you mix red and yellow, you get this orange color. So this is how we describe colors in space. But generally, when we're talking about color measurement, what we really want to know is what's the difference. So you can calculate the difference in your L value between standard and sample, so you can determine whether your sample is lighter or darker than the standard. If the delta L value is positive, your sample is lighter than the standard. If it's negative, your sample is darker. Similarly, with the delta A value, you can determine whether your sample is redder or greener than your standard. And with the delta B value, you can determine whether your sample is yellower or bluer. So you can look at these individual values, these individual different values to learn certain things about your color. But what we really want, what really makes life easier, is to have this DeltaE value. This is what we call the overall color difference. And so it's calculated like this. You take the difference in the L value squared plus the difference in the A value squared plus the difference in the B value squared. And this is actually just the distance formula in three-dimensional space. So if you were to plot two sets of LAB coordinates and actually measure the distance between them in LAB space, that's what you're calculating with the DeltaE star value. And so that's a single number that tells you the overall color difference between sample and standard. And that's better than having to look at three values. Whenever possible, we want to, just look at one value, have our pass-fail criteria on one value rather than three or more. That just makes things a little bit easier. So we really like to use the DeltaE value to calculate overall color difference and to set the tolerance on that to say if the DeltaE is above this much, it's an unacceptable match. If it's below this much, it's an acceptable match to the standard. So in addition to LAB space, or LAB coordinates, I should say, we also have LCH coordinates. Now this is just a different way of describing the same color in the same color space. So LAB and LCH, these are the exact same color space. It's just a different way of describing your color. So LAB is what we refer to as rectangular coordinates, where all of the axes are perpendicular to each other. LCH is what we would call a polar coordinates version of these color coordinates. So L is the same, it's still the vertical axis, but now instead of having A and B values, you have a C value, which stands for chroma. And chroma is simply a measure of, you could say, how much color or how deep the color is or how saturated the color. The higher the C value, the more chromatic the color is. And so the C value tells you how far from that center axis your color is. So the further out from the center, the more chromatic your color is. So an example of a very chromatic color would be like a scarlet red or like a forest green. Whereas like a beige or a gray or off-white would be a very achromatic, a low chroma color. So we have the L value, the C value, and then the H value. H is the hue angle, and that tells us what the hue of our color is, red, green, yellow, whatever. And that angle is counted off of the positive A axis. So the positive A-axis is 0 degrees. So if your color has a hue angle of 0 degrees, that's a red color. And then you count up as you go counterclockwise. So the positive B-axis has a hue angle of 90 degrees. The negative A-axis is 180. Negative B-axis is 270. And then you get all the way up back to 359.9, which would be, again, a red. So you can describe any color on this color wheel by that hue angle. So now instead of using LAB, we're using LCH, but we're describing the same color here as we did before. So the L is still 58, the lightness is still 58. The chroma value is positive 47, well, 47 chroma values are always positive, but that's a fairly high chroma value, so we would say this is a very chromatic color. And the hue angle is 38 degrees, and so we know that 0 degrees is red, 90 degrees is yellow, and we know this is somewhere between, about halfway between, so we know that the middle between red and yellow is going to be, again, an orange color. So same color space, just different set of coordinates. So typically, the reason we have two different sets of coordinates for describing colors in the same color space is that typically we will use LAB values and LAB tolerancing when we're talking about achromatic or non-chromatic colors, which we consider to be colors with a chroma value less than 10. And for chromatic colors, which we define as colors with a chroma value greater than 10, we use LCH tolerancing. And I'm going to show you why. So here we have a bunch of samples. We have a standard right there in the center, that double triangle thing. And then we have a bunch of samples that were sorted visually into visually acceptable compared to the standard and visually unacceptable. So we have, so these samples were then measured and plotted in this AB space, AB plot. And so those gray circles, those are the colors that have been assessed to be visually acceptable to the standard. And the ones with the red X's, those are the visually unacceptable samples. So if we draw a shape around the visually acceptable matches, we get something pretty close to a circle, or if we were in three-dimensional space and we added in the L value, the L axis, it would be a sphere. So if we want to do LAB tolerancing, we can apply box tolerancing to this. Box tolerancing is what we call it when we use A and B tolerances, because when you tolerance on the A and the B value, you get a box like this. And we can see that this box approximates that circle pretty well, so that we're accepting all of our visually acceptable matches and we're rejecting all of our visually unacceptable matches. Now that was for an achromatic color. This is a color with very low chroma, but now we're moving to a color that has high chroma. So this is a very chromatic color. And if we do the same thing, if we sort these samples into visually acceptable versus visually unacceptable and plot it in AB space, what we get is this ellipse. So now if we try to apply AB tolerancing to this ellipse, we get something like this. And so now we are accepting, we're instrumentally accepting all of our visually acceptable matches, but now we're also going to be accepting a lot of those samples that don't look very good compared to the standard. So you're going to be shipping product that doesn't look very good, which of course we don't want. So how do we fix this? Well, one thing we could do, we could always just make the tolerances smaller. So now I'm not accepting any visually unacceptable matches, save for that little outlier there. But I'm also rejecting a lot of visually acceptable matches. So when you reject matches instrumentally that actually look good visually, it's going to cost you money. You're going to reject product that is actually good, and it's going to cost you money. So neither of these things are very desirable. So what do? We apply LCH tolerancing. So that ellipse is almost always going to be oriented towards the center of LAB space. And so we can set tolerancing on the H value, the H angle, the hue angle, and the C value, the chroma value. And what we end up with is this sort of pie slice type shape that fits better and is oriented better to fit this ellipse that describes our visual acceptability for this standard. So this is why we typically switch to LCH tolerancing. We recommend using LCH tolerancing for chromatic colors, because the visual tolerance ellipse for those colors, or the visual tolerance shape for those colors, typically forms an ellipse, and the LCH tolerancing is going to approximate that ellipse better than box tolerancing with LAB. So back to the DeltaE value, the overall color difference equation. So this DeltaE value that's denoted with that asterisk, what we call DeltaE star, this is the equation for DeltaE star. It's that basic distance equation in LAB space, and it's probably the most commonly used difference equation, but it's not necessarily the best one. And so here we have an example. We have a sample compared to a standard, and we can see that there's a 0.57 unit difference in the L value, 0.57 difference in the A, and 0.57 difference in the B. So all of the color difference is split evenly among the three values, LA and B. We plug those into this DeltaE star equation, and we get a DeltaE of 1. Now we take this other sample, And we plug those difference values into this equation. So we can see here that there's zero difference in the L values. The L value is exactly the same between sample and standard. The B value is exactly the same between sample and standard. The only difference is in the A value. But when we plug that into this equation, we get delta E of 1, same as for sample 1, and yet visually we can see that sample 2 looks further from the standard than sample 1. It's not as good of a match. So this sort of just illustrates that the delta E star equation is not completely visually uniform. It can mean different things depending on what color or whether the difference is in the L value or the A value or the B value, things like that. So to further sort of illustrate this concept, so here what we're looking at is a slice of the LAB color space. We're looking at the AB plane. So in the center of this circle, we have neutral or achromatic colors. And as you go outwards, you get to more chromatic colors. And we can see in this color wheel lots of these ellipses. Now these ellipses represent visual color tolerances for the standard in the center of each one. So in the center of each of these shapes, you can see a tiny little dot. That's the standard. And so the idea here is that any other color within that same ellipse will be visually indistinguishable to the standard. And any color outside that ellipse, we would be able to see a color difference. So you can see that depending on where you are on this color wheel in the slice of LAB space, those visual tolerance shapes change size and they change shape depending on where you are. For example, the achromatic colors tend to have much smaller visual tolerance shapes than the more chromatic colors. And that's what that tells me is that we are visually more sensitive to small shifts in color for achromatic colors than for chromatic colors. And you can also see that even if you look at all the very chromatic colors, the shape of the ellipse is going to change depending on what hue you're looking at. So for example, the greens over to the left have very wide, fat ellipses. And that tells us that we have visually very large tolerances for shifts in hue for green colors. But for example, those orange colors at the top right, those ellipses are very, very skinny. And that tells me that our visual tolerance for shifts in hue for orange colors is very tight. We're going to very easily be able to tell small shifts in an orange color much more easily than a green color. So the size and shape of these tolerance ellipses depends on where you are in this color space, and so we need a color difference equation that can account for that. So the goal here is to have better agreement with visual color perception, and ultimately we'd like to have one tolerance for all colors, meaning a uniform color space. So with the delta E star equation, if you're calculating the delta E value for 2 green colors, you might get a delta E of 3, and that might look fine to you. Visually, that might look like a good match. But if you're calculating that for, say, a gray color and you get a delta E of 3, that color difference is going to visually look much larger. So with delta E, you have to have different tolerances depending on what your color standard is. And every time you get a new standard, every time you produce a new color, you have to determine what the color, the tolerance is going to be for that. So ideally, we'd like to have a color difference equation that is more uniform and where we can have one tolerance for all colors, where a delta E of 1 is going to visually look the same for a green color as it does for an orange color as it does for a gray color. So the first sort of widely accepted improvement to the delta E calculation, the delta E star calculation, is called DeltaE ECMC. It was developed by the Color Measurement Committee of the Society of Dyers and Colorists. It was based on visual evaluation of textile samples. So we're talking about fabrics, things like that, very low gloss matte samples, currently specified in international standards. It's based on elliptical spacing and LCH, not LAB. And it corrects for chroma, hue, and lightness dependent on perception. So it's a modification of the DeltaE equation that includes weighting factors, the SL, SC, and SH numbers, which modify the calculated color difference value depending on the standard, where the standard is in color space. And then you have application factors L and C that modify the lengths of the axes in this ellipse. So if you want more tolerance in the L direction, you can increase the L value or the L factor. If you want more tolerance in the chroma direction, you can increase the C factor. So SL, SC, and SH are defined by the equation. The L and C factors are defined by the user. And here's what that equation actually looks like. I'll let you peruse this on your own time, but the important thing to see here is that the SL, SC, and SH values are determined by the color of the standard. That L1, C1, those are the values of the standard, and those are incorporated into this equation. And then, of course, you have the L and C factors, which are determined by the user again. So that brings us to our next color difference method, which is DeltaE 94. This is based on visual evaluation of a new sample set using solid colors only. So this was evaluated using glossy painted panels rather than textiles. Currently published in the following CIE recommendation, again based on elliptical spacing and delta LCH. It corrects only for chroma-dependent perception of chroma and hue, and there's no lightness correction. So this is what the DeltaE 94 equation looks like. So again, we have those SL, SC, and SH weighting factors, which are determined by the position of the standard in color space. And then we also have the KL, KC, and KH factors, which again are determined by the user. So if you want to adjust the equation for your own needs, you can do that as well. So here's an example of some yellow colors. We have a standard and then 3 samples. One of these samples is shifted in the positive C direction, so it has slightly higher chroma than the standard. Another sample has less chroma than the standard, and the third sample is shifted in the hue direction. So we can see the calculations up there on the table. We can see the color difference calculated under DeltaE star versus DeltaE 94, and we can see that those color numbers, the difference number, goes down considerably when you switch from DeltaE star to DeltaE 94. And what that's telling me is that, take that first yellow sample with a DeltaE star value of 3.52, that's kind of a misleading value. If I heard 3.52, I would think, oh, that's a pretty big color difference. But when you switch to DeltaE 94, you see that it's only 0.71, and I know that's corrected for the position of that standard in color space, and that's probably a more accurate accounting of the color difference. This is a very, very chromatic color, and we know that chromatic colors have larger tolerances, larger visual tolerances than achromatic colors, so that DeltaE 94 calculation will go way down. But we can also see that if we look at the first 2 samples, yellow plus C and yellow minus C, versus the last one, the yellow that shifted in the hue angle, when going from DeltaE star to DeltaE 94, the yellow minus H doesn't go down by quite as much as the ones that are shifted in the chroma direction. And that's because we have larger visual tolerances for shifts in chroma than we have in hue. So we're more easily able to distinguish small shifts in the hue of a color rather, more than chroma. And so that causes the DeltaE 94, that shift in hue causes the DeltaE 94 value to be a bit higher than the ones that are shifted in chroma. And here's one more example of DeltaE star versus DeltaE 94. So we have a pair of reds, brilliant reds, and then we have a pair of browns or dark reds. And we can see that the difference between DeltaE star and DeltaE 94 for these two. So DeltaE star for the brilliant red is about 2.5. Under DeltaE 94, it goes down to 0.62. For the brown color, it has a DeltaE star of 3.06. And then under DeltaE 94, it goes down to 1.07. So that doesn't go down quite as much as for the brilliant red color. And the reason for that is because if you look at the C value, the brilliant red standard has a C value of 80, and the brown standard has a C value of 41. And again, we have larger visual tolerances for more chromatic colors. So with that brilliant red, our eyes are going to be a bit more forgiving of differences in that red color, and so is the DeltaE 94 equation. Whereas the brown, since it has lower chroma, it's not going to be as forgiving for differences in chroma or anything as for higher chroma colors. Okay, and that brings us to DeltaE 2000. You see it denoted as DeltaE 00. This was based on several already existing data sets, namely the same one that was used for DeltaE 94. So this equation is actually a further improvement on DeltaE 94. There was no new set of samples evaluated for this. They just used the existing data. Published in this report, again, based on elliptical spacing and LCH. But this one, unlike DeltaE 94, this actually has 5 corrections to the DeltaE star equation. It corrects for lightness, chroma, and hue-dependent perception. It has a rotation function, improving the performance for blue colors, and it has a factor for rescaling the A-axis, improving performance for gray colors. So again, we see this DeltaE 2000 equation. It should look pretty similar to the equations for CNC and 94. You have the KL, KC, and KH, which are the user-defined factors, and then the SL, SC, and SH, which are the weighting factors defined in the DeltaE 2000 equation. But then you also, over to the right, you have a rotation function to improve tolerancing for blue colors. And I'll get into exactly how that works in a sec. Okay, I'll get into that right now. So if you think back to that color wheel that had all the visual tolerance shapes, the visual tolerance ellipses in it, and they were all, I explained how they're all different sizes and shapes depending on where you are in that color space. But if they all had one thing in common, it's that the major axis, the long axis of each of those ellipses was always directed towards the center of LAB space. And we came to find out through, visual studies that that's not exactly true for blue colors. For blue colors, that tolerance ellipse is actually tilted a bit. And so that's what that rotation function is for more accurate tolerancing, specifically in the blue range. And so you can see here a standard versus a bunch of samples in DeltaE 94, under DeltaE 94 versus DeltaE 2000. And with DeltaE 94, you have that ellipse, which is oriented straight towards the center of LAB space. And based on that tolerance ellipse, we can see that most of these samples are intolerant, according to the DeltaE 94 equation. But if we look at DeltaE 2000, we can see that that ellipse is rotated a bit, because again, we found that to be a bit more accurate compared to what we see visually. And we can see that once that ellipse is tilted to make it more accurate, a lot of those samples that were previously intolerant under DeltaE 94 are no longer intolerant. So in addition to that, there is a modification of the A value. So DeltaE 2000 uses weighted color values, L prime, A prime, B prime. So not just the DeltaE value is going to be different, but the actual L, A, and B values are recalculated under this equation. And they're recalculated, you can see over the left here how they're calculated. So L prime is just equal to L star. B prime is equal to B star, so there's actually no modification for L and B. But there is a modification for the A value. And A prime is equal to A star times 1 plus G, and you can see G below. And so this is for colors with very low chroma, so neutral or achromatic colors. It was found that the tolerancing for A colors or the color differences in A colors weren't quite matching up visually, and that A value needed to be stretched a bit. So you can see that in this G equation, you have the chroma value. So the A value is directly related to how much chroma or how high the A value is. But for very large values of chroma, or very large A values, this equation is going to be equal to 1. So this modification of the A value is only applied to very low chroma colors, and as you get to larger chroma colors, that modification goes away. And that is all I have for you for my presentation. And so I will pass things back to John for our Q&A.
Thank you, Corey. Very good. Lots of great information there. Couple questions too. Yes, we are recording this, and we'll be sending out the link as well as a PDF of the presentation in the next day or so. So you will receive that information. Now, getting right into the questions here from Frederico, are the max values of A and B equal to 100?
Good question. I believe theoretically they go to 100. I think in practice you never actually see values that high. But yeah, I think 100 is the theoretical limit.
Okay, thank you.
Also,
another question.
Also added on.
Oh, great.
Also added on to that, it's not balanced. So the three-dimensional color space is oblong, and you can get higher values in, say, yellows than you can in blues.
Okay, thank you. Next question here from Aaliyah. Is there a conversion that directly relates A and B values to C?
Yes. A and B to C. It's a fairly simple conversion. It involves I want to say the tangent of the hue angle. Yeah, there is a very simple conversion between LAD and LCH. I don't think I have it on hand right now, but if you'd like to email me, I can send those to you.
Corey, it was on your last slide.
Sorry?
It was on the last slide where you're talking about DeltaE 2000.
Was it?
Right there.
It has the hue, oh wait. Yeah, it has the hue angle. But not the
Do you have one before or after that? Nope.
I don't think so.
Right there.
Oh, there it is. Yeah. Oh, yeah, okay. C equals square root of A squared plus B. Okay, yeah. So that's, what is it? Pythagorean theorem? C squared equals A squared plus B squared, because A, B, and C form a triangle. Yeah. So it's the hue angle that involves the inverse tangent. And the C is just, yeah. Okay. Thank you, Greg.
All right. Thank you, Greg and Corey. How about that? Next question from Kasim, and I apologize if I'm mispronouncing anyone's name here. Is there any new color equations? Are there any new color equations?
So as far as I know, I mean, there probably are newer ones. I think for solid colors, DeltaE 2000 is the newest widely accepted color difference. There are newer equations for multi-angle colors, for colors that are measured with a multi-angle spectrophotometer. There are specific color difference equations for measuring at multiple angles. And there are newer ones in those, like DeltaE Audi and things like that. But for solid color, I think DeltaE 2000 is the newest one.
Okay, great. Question here from Richard. Let's see, what about the effect of gloss on color perception? Are there equations that treat color space as a four-dimensional space to account for the gloss value?
There are not. So that really, the way that gloss influences our perception of color is really, that's captured in the geometry of your spectrophotometer rather than in the after measurement calculations. So there are two main geometries of solid color or single angle spectrophotometers, 45-0 and sphere. 45-0 measures color as we see it. So glossy surfaces typically appear darker and more chromatic to our eye. And with 45-0 instruments, that will be reflected in the color numbers. So it will be measured as being darker and more chromatic, whereas sphere ignores the gloss and only measures the pigmentation. So there is no numerical conversion. There's no way to convert LAB values taken with a 45-0 instrument to LAB values taken with a sphere instrument. You just have to choose the correct spectrophotometer for your application, whether you want to see, whether you want to measure color as you see it with gloss included, or you want to just measure the pigmentation exclusive of the gloss or surface texture.
Okay. Richard, I've unmuted you. Did that answer your question? Richard, are you there? Okay. Okay, great. Thank you. Next question here from Jason. We used several adjectives to describe chroma. Would a fair synonym be intensity?
Intensity. As sort of a layman's way of speaking, I guess you could call it. I mean, none of the descriptors I used, saturation or deepness of the color, none of those are truly accurate. They all mean different specific things. So in common terms, we can, speak of a color as being more intense or being deeper and things like that. And we kind of know what that means. Intensity, personally, when I think of intensity, I think of how much light, essentially, how much energy is in the light, which I would say relates more to lightness, technically, than the saturation of the color. But in common terms, it's whatever's acceptable to you, whatever helps you get your point across.
Okay, thank you, Corey. Anyone from our sales team or business line manager team run into common questions when it comes to equations that they'd like to share? Or if anyone else on the line too has a question, just log it in the Q&A box and we'll get right to it here.
So one question that comes up a lot is, which color difference equation do I choose? Is, one clearly better than the other? And I'd say that a lot of it has to do with what type of material that you're dealing with. And the sample sets that were used when evaluating or when creating these difference formulas. So DeltaE ECMC was created by evaluating textile samples, whereas 94 and 2000 were created using solid colored glossy painted samples. And so if you're dealing with textiles, probably CMC would be the way to go. Whereas if you're dealing with paint or glossy plastic or something like that, probably 94 or 2000 would be better. And similarly, going back to automotive difference equations, the reason you measure colors at multiple angles is because it has special pigments in them, like metallic pigments, aluminum flake, and so the equations for multi-angle color were evaluated using effect pigments, colors with effect pigments in. So the sample set counts for a lot when choosing which difference equation you use.
Great, thank you. Which equation is best for non-chromatic colors?
For non-chromatic colors, probably 2000. Because then you would get that correction on the a-axis that makes it a little more accurate compared to the visual. Okay,
thank you. A question from Jody here. Let's see. What type of spectrophotometer is recommended for measuring matte finish silver?
Matte finish silver. You could use either of the major geometries, 45-0 or sphere. Probably not going to be a huge difference between them since it is a matte color. But if gloss differences is something you're concerned with, if maybe one batch has slightly higher gloss, the next has slightly lower gloss, and you're just trying to match the look of them, 45-0 would probably be best for that.
Okay, great, thank you. Another question here from Brian. Are you able to share similar formula explanation for DIN 6175? What makes it different, unique, better, worse than Delta 94, DE 94, or the DE 2000, specifically for automotive gonio apparent colors?
Right. So again, as I mentioned, part of it is the sample set. So DIN 6175 is developed using metallic coatings. So that's typically better when evaluating metallic coatings, but also it has, it calculates the DeltaE value independently for each angle. And it actually incorporates the angle into the measurement angle into the equation. So typically with metallic colors, you might read at anywhere between 3 and 6 angles. And so it's going to take the actual angle into account when calculating the difference.
Brian, I'm going to unmute you here. Did that answer your question, sir? Are you there, Brian? You're unmuted. Did that answer your question?
Apparently, I was still muted on my end. Yes. My specifically, I was hoping to be able to see some type of graphic of how that changes the shape of the ellipse related to. We've been using the DeltaE 94, and we have some supplier who's been using the DIN 6175, and so we've kind of been talking to us about it. We've been looking at studying it, but I haven't really been able to find that kind of detail that explains how that, like the examples you gave where you had the square box tolerance versus the ellipse and how you had the rotational component on one of the formulas. That type of thing was really helpful to visualize what's going on. I was hoping to find something like that.
Corey, do you have anything in your bag of tricks?
Yeah, so we have actually done a few web seminars specifically on automotive difference equations. John, do you know if we have any of those recorded?
Yeah. All of them. So Brian, let me, after we're done here, let me go back, dig up those recordings, and I will send you links and passwords so you can look at those past webinars.
Oh, that would be fantastic. Thank you very much.
And if you have any questions, you can of course email me.
Okay, great.
Yeah.
Thanks.
Wonderful. Okay, next question from Frederick. My customer that supplies parts, steel bumpers for trucks, to OEMs, still using LAB tolerancing. Shouldn't they be using something more current?
Steel bumpers for trucks. I'm going to say if that's all they do, it's probably not as big an issue because everything they make is probably pretty close to the same color. So that might work, LAB tolerancing and DeltaE star might work a bit better for them than for a manufacturer that's dealing with a wide range of colors. I'd say, CNC 94 2000 are always going to be a bit better than DeltaE star, but yeah, I don't think it's crucial for someone who's only making one type of color to switch to that.
Okay. Great, thank you.
So
go ahead, Greg.
One other popular question that comes up is, especially say for people making paint or plastic, where they talk in terms of LAB distances, and they have history of knowing how much a certain add will move a color in LAB color space. A lot of times people ask if they switch to these elliptical tolerancing systems, can I still get access to the LAB values, or is everything always in LCH? And you get access to all of those values all the time. So it's just how the tolerance gets built in LCH coordinates.
Okay. Frederick, let me unmute you here. There you go. Did that help? Or any follow-ups?
Yeah, can you hear me?
Yes, sir.
Yes, I was just curious. They don't really use it too much, but to me, it just seems kind of antiquated. Most places seem to use the CMC tolerancing. So that's why, as far as for initial color submissions, I think it's usually correlates better to what you visually see. And then instead of going by just the LAB tolerancing. But that's what they've been using ever since. So. And with, again, like you say, on the trucks, it's not matching right up to the surface. It's not like a plastic fascia or something, so it's not real critical, but still.
Mm.
It just seems like they would use something a little more modern. I don't know if the OEMs have specifications of what to use or.
I have a suggestion, actually. So this is Geraldine Camp. The hard part really is getting started and making changes. And always, you know, when we're teaching these kinds of things to customers, we always encourage them to go to the latest color tolerancing equation. DeltaE 2000 being the latest is so far still yet the best because it does apply that, you know, the tilted ellipses for the blues, which, you know, humans see those differently. The problem is getting people to change and not making, you know, having them understand that they can make these changes and still continue their old process. It's just collecting more data for a time being because the history is there. And you want to be able to collect the data long enough in conjunction with them trying to make the change so people can start wrapping their head around the differences. So if they're using DeltaE star or CMC and they want to jump into the now, all they need to do is continue doing what they're doing, but then also do the measure and the calculation using the latest equation. I don't know all of the software programs that, you know, all of the instruments that are out there have and how easy it is to see both of those. But I can tell you in our software, you can actually do an easy conversion. You can make a copy of any test series or any sample measurements you've just taken and can take that whole thing and copy it in the software and then convert it over to a new equation. And you can see right there on the screen exactly what that did to your color tolerancing and whether or not it made sense. So I know that it's easy to do, but you know, having customers start to incorporate new equations, that takes time because they have to have some history for comparison. So that's, you know, you can't just cut off old things. You have to incorporate new and then eventually decide maybe in 6 months or so to stop doing it the old way because now you're comfortable. So I agree with you. Trying to jump into the now the hard part is just getting started, really. Does that help?
Yeah, I guess as I tried to explain it a couple of times when I showed them the difference between the Delta CMC as far as it's supposed to, it more closely mimics what you're seeing visually. So it gives them a better idea and try to help keep them out of any trouble I have call outs for something being off color, which is rare. But
well, the thing you might want to bring up maybe is this DeltaE CMC was actually originally designed for the textiles industry, and it was adopted eventually into paint and coatings. But the reason why there's newer equations is because the textile industry does not translate very well to paint and coatings. So we had to come up with something a little bit different than CMC because it just didn't work visually. So it was originally for the textile industry, and the textile industry still uses, a lot of them still use CMC.
oh, okay. All right. Thanks.
You're welcome.
Oh, sorry, guys. Talking to myself on mute here. Next question from Rick here. Does your software give a good visual 3D view for the elliptical tolerancing?
It does not give a 3D view, no. It does give a plot. It has the AB plane next to the L value, but no 3D visuals.
Okay. Next question here from Mark. I think all of these are for small color differences less than 5. If we're using big DeltaE, more than 5, would DE-CIE be better than DeltaE 2000 or not? Want me to read that again?
I'd say you would still benefit from switching to one of the newer equations. I would think that those differences are going to even be exacerbated when you're talking about larger DeltaE values. So, you know, with DeltaE star, you might calculate an 8 and a 5, and with 94 2000, it might be, you know, 1 and 0.8, or probably larger than that, but you get the idea. So, yeah, I'd say you would still benefit even with larger DeltaEs by basing the difference on the standard and where it is on color space rather than just using LAB values.
Okay. Mark, did that answer your question? I'll unmute you here. You there, Mark?
Yeah, it did.
Okay.
I just did a comparison with the old format and this one. It's like there was, like you already said, there's a big difference. It's two. People
Your audio is pretty muted on our end here, Mark.
Oh, sorry about that.
Oh, that's better. Hey.
Can you hear me? I'll cut my hands around the mic.
Yeah, much better.
We just have people who we have been using the CIE, and you know, there's been some questions about moving to 2000, and you know, they're wondering, well, how are those values going to compare with what we're used to, and you know, they're now like actually achieving something different. So they're reluctant to change. Just wondering if there's just any reason for it. I mean, especially when I look at the recommendations, they say that you know, these color difference metrics are really only validated for small color differences, not our color differences.
You're breaking up again, sir.
Sorry, our color differences are like 20 to 30.
Okay.
Wow. It's big.
Yeah, they're for stain removal.
Yeah. Interesting. And you had another question down here too. You want to ask that now?
Yeah, I've been hearing for quite some time about a new color model called ECMC that takes into account the surrounds and stuff like that. And, you know, they've been working on it forever, and I'm just wondering if that's ever going to be the successor to DeltaE 2000.
What is it called?
ECMC, CIE CAM02.
ECAM2. No, I'm not familiar with that. Is anyone else on the line know about that?
If it's taking into account the surround, it's going to probably include some BRDF measurement for including that, and we do that in the refinish space. We've done some work on that to then display the colors with the different surrounds. So it looks different on the screen, but you still have to start with multi-angle color measurement, because as you change the angle at which you illuminate and detect, if you have any color travel, you need to capture that also. So it captures color travel, it captures sparkle and graininess, and then puts that on a, you can then display that color, and then if you want to add surround, it's another factor that gets factored into it. But we can follow up with you separately on that.
Okay.
Yeah. All right. Thank you, Mark. We have another question here. Any luck with getting Mercedes to adopt the DeltaE model?
What was the question?
Is there any, have we had any luck getting Mercedes to adapt a DeltaE model?
I don't know. Greg, you know anything about that? Sideways on the line. Yeah.
Greg's on mute.
I think that's something
you would need to unmute again. But Ray Roby, our business line manager, is not on with us today. But I understand that we are always working with the OEMs to try and get them to adapt the latest models, or at least develop with them a color tolerance and model. But yes, I mean, we're always working worldwide with the OEMs to adapt. So we can't answer right now the process or the stage, or whether or not we're successful in that, you know, with Mercedes right now. But you know, we can follow up with that question as soon as we talk to Ray Roby, our business line manager.
Great, thank you. Any other follow-up questions? You know, reminder, we'll send out the presentation along with the link to the recording after the fact. If you have any last questions, enter them in the Q&A box and we'll get to them. And if not, that's all right too. Just give it a minute or so here. All right, well, it looks like that's it for today. So just I want to thank everybody for attending, for the discussion, for your questions. We'll get this information out to you. Also, be on the lookout for additional invites for office hours and our 60 minutes seminar session that typically is a longer presentation and shorter dialogue. So stay tuned for those. And as always, if we can help in any way, shape, or form, please reach out to myself. I'm in the marketing group, John Kowalski. Corey, you see his email on the screen right now, corey.cohen@altana.com, or any of your regional sales managers. We're here to help and support any challenges you have. So with that, thank you very much, and enjoy the rest of your day. Thank you.
Thanks, everyone.